Hi everybody. So today's video is going to be about Sierpinski's triangle, which is this little fractal here. Now this is a very popular fractal, a lot of people might have seen it. It's quite common in like general artwork and stuff. The way the fractal is formed is I take a triangle and then I take a smaller sort of upside down triangle and put it inside of it. And these are all equilateral, I'm just drawing them very poorly. And then inside of the gaps that I leave, I will be drawing another triangle that fills the gap perfectly. And then again here I've created 9 gaps, and so now inside of each of these 9 gaps I'm going to draw another triangle. And I won't keep doing it, but you can see how the pattern's going to continue, and eventually this space is going to be full of an infinite amount of triangles. And we can see here we've got these steps, step 1 to step 2 to step 3. See, we just keep adding in these white triangles onto my black shape. And as the shape goes on, it gets more and more white, and the black bits seem to get thinner and thinner and thinner. This looks infinite. I mean, it's not, just a level 8 down, but we can't really see deeper than that. But the idea is that in principle, this could go on forever. Now, the key insight you need to have with Sierpinski's triangle is that it has a property called self-similarity, which means that if I take one part of the fractal, namely this bit, at an infinite depth, this is actually going to be equivalent to the shape itself. So it's a shape made up of smaller parts of itself, which is a special kind of fractal. It's a recursive fractal. Now this video is going to be more about how Sierpinski's triangle seems to appear in random places in mathematics, places where it doesn't really feel like it belongs, where it wasn't really invited. So I'm going to start with the most basic example. This is the one you're more likely to have heard of in the past, which regards something known as Pascal's triangle. So if you haven't heard of Pascal's triangle, I'll quickly explain what it is. This is to do with binomial coefficients and combinatorics and stuff, so it's a very different field of math, but the idea is that we have a triangle, and let's say it starts looking like this. And my rule is that to place new numbers into my triangle, I'm going to sum the two values above them. So 1 plus 1 is 2. And we can sort of imagine there's a 0 here and a 0 here. So these are going to sum to 1. The 1 and 2 sum to 3. 2 and 1 sum to 3. And then we've got 1 here, 1 here. And we keep going. Now it's going to be 1s on all the sides. So we've got 4 here. 3 and 3 is 6. You'll notice that this triangle has a clear line of symmetry, which makes sense. Now I'm not going to draw the whole thing out because that would take too long. So instead I've got an image of it prepared that I'm going to bring over. So here's the image here. Oh, not that one, sorry. Copy, paste. Here we go. Yep, this is Pascal's triangle. Now, really simple thing I'm going to do to Pascal's triangle. I want to color it in. Now, it would be very boring to color it all one color. I'll just get a big green triangle. So instead I'm going to set some rules. I want to do 2 colors. So a very reasonable way to break up numbers into 2 categories is evens and odds. So my rule is going to be that if a number is even, I'm going to color it in green. And if a number is odd, I will color it in, let's say, orange. And let's just see what happens. So I'll start by coloring in some of the odd ones. So these 1s are all odd. I won't go all the way down just yet. That 2 is an odd, the 3s are odd, 5 is odd, and we'll go 15, 35, 15, 35. Now this whole row is all odd. And I'm actually just going to start speedrunning this a little bit. So these are all odds all the way down the lines. These are all odd. We've got a full line of odds here with these and these and these. And now let's keep going. So we've got 9, 45, and all these numbers look odd down to here. And because we know Pascal's triangle is symmetrical, we know that we're going to be copying the pattern on the other end. Those are both odd, which means these are both odd. Now, these are all odd as well. Cool, alright. So we're basically done here. That leaves the even numbers, which I'll just quickly fill in. So we've got singular even numbers all throughout here. And hopefully you can see at this point what I'm getting at. This is Sierpinski's triangle, which is really, really weird. Now, there's a lot of interesting intuitions for why Pascal's triangle and Sierpinski's triangle is so linked. But one thing I want you to think about and keep thinking about throughout this video is this idea of even and oddness, or parity is what we like to call it. But the parity of the numbers. It was this even and odd idea that seemed to bring out this triangle. So I'm going to do a couple more examples of Sierpinski's triangle being found sort of in the wild. And I want you to keep this even or odd idea in mind, because they're all going to be in some way related to this concept. And I suppose what I'm going to try and argue here is that this idea of even and oddness, or true and falseness, or zero and oneness, is going to be inextricably linked to the Sierpinski's triangle shape. So yeah, let's get into the second one. Now for my second example, I'm going to do something quite similar to Pascal's triangle, but this time it won't involve numbers, and it would just involve light switches, things that are either off or on. And if you want, we can think of it instead of off and on as true and false. So I'm going to bring in another image here. And this is just going to be a blank array of hexagons that we're going to draw onto. Here we go. Now let's define some rules. So let's say that I'm just going to use blue here as a backdrop. Let's say that every cell has two states, either true or false. Now, if something is false, we will make it white. So far everything is false. And if something is true, let's make it green. Oh no, let's go red. Oh, red actually feels like it should be false. Let's make it orange. It's gonna be true. Alright. And we're gonna use what's called an XOR gate. Now, for those of you who are familiar with binary logic, XOR means exclusive OR. It just means that it's going to be true if one of the inputs are true and one of them are false. So this is sort of like a function that takes in two true or false values, or booleans, and outputs one boolean. So let's quickly draw up an XOR table. So let's say I have, these are my inputs, so A and B, and then here we're going to have A XOR B. And instead of using ones and zeros, I'm just going to use whites and oranges, which I already have. So let's say A can either be, we're just going to leave it blank to be white. So all different combinations are going to be A can be false or true, and B can be false and true. So you see here, these are our four situations. And now we're going to give our outputs. So remember, an XOR gate will return true if one of them was true and one of them was false. So this will return true, this will return true, and the others will return false. If I want, I'll just put a little line here to mean false. Now we're going to use these XOR rules to fill out this grid of hexagons. For any two cells, like these two, the cell underneath them, its color is going to be determined by putting those two cells into this XOR table. So right now, the entire shape is stable because everything's false. And if everything's false, then that means that for every two cells, their child has to be false, because false and false gives me false in my XOR table. So this is fine. This is a completely stable situation. Let's consider other stable situations. So I'm going to change it a little bit by just adding one true thing. I'm going to violate the hexagon a tiny bit by adding one truth here. So now this cell's been set to true. Now if this cell has been set to true, we need to make some updates. Well, this cell here now has one true and one false parent, so it also needs to be set to true. And the same is true here. And the same is true here. And in fact, it's going to be oranges all the way down now, because all these cells have one true and one false parent. And the same thing is true on this end. And now let's do the same thing sort of in the middle. Well, this cell here's got one true, one false parent. This one's got one true and one false. Now, these three have parents that are both true. And if both things are true, the child will be false. So these can actually stay blank. And now it should be very clear what I'm getting at again here. I fill in this triangle, and it's going to be exactly the same as what I got before. I won't do it all the way, but this is the gist of it. We'll make these ones black so that you can see them easier. I've got a triangle here, and a single, and a single. And if I keep going, I will end up with something like this. So once again, there's a Sierpinski's triangle that appeared seemingly out of nowhere. And all I needed was this XOR rule. Now, one interesting thing is to change this rule, or change this chart, and see what different shapes you get. That might be a different video, but that's something you can definitely do by yourself. If you're into, artwork and math, it's a fun little exercise to just change the rules and see what you get. If you're familiar with John Conway's Game of Life, it applies something similar to this, but on a square grid and with a concept of time, where cells can live and die, and we have different steps. This is just a static image, so there's no element of time here. But again, Sierpinski's triangle has arisen. This is very similar to the Pascal's triangle odd or even idea, because the rules of adding, because if I add two even numbers together, I get an even number, and two odd numbers make an even number. But then if I add one even and one odd, I get an odd number. And if I replace true and false with even and odd, that basically gives me these rules. So that's why Sierpinski's triangle has appeared here again. Cool, alright, now I'm going to go on to my next example. Now, my next example is going to involve less of an explanation, partly because I don't feel qualified to explain it. But I will give a basic diagram, and I actually have a little program to run to show this thing in action. So, imagine taking in a triangle and just defining it by the 3 points on the outside of the triangle. So I don't really care about the triangle itself. All I care about is that it's got 3 points. I wonder if I can just draw, I'll do my best here to draw an equilateral triangle. And let's say that this triangle has 3 corners as they do A, B, and C. Now all I'm going to do here is I'm going to pick a random point inside the triangle and color it in. Now what I'm going to do is I'm going to pick a point at random, A, B, or C, and consider the line from that point to that corner. So let's say I randomly pick B. I draw a line from here to B. And in the very middle of that line, I will be placing my next point. And now again, I'm going to pick a random corner, A, B, or C. Let's say this time I pick C at random. I'm going to connect it to here, and then I'm going to put my next point right in the center of that line. And I'll do it one more time. Let's say, I'll pick B again randomly. Now I draw a line to B, and halfway through that line I put a point. Now, I've got some software that does this quickly. Let me just pull it up. Oh, I might have given it away a bit there. If I hit +1, hopefully you can see it, but we're adding dots slowly with this process. Now let me add 100, and 100 more, and 100 more, and now I'm just going to let it run. We'll go until we get 100,000 points drawn. Currently I've got 60,000 points that have been drawn. And I mean, this is kind of crazy. This I don't really understand, but those were really simple rules. They felt quite well, they were incredibly simple rules, and they drew this triangle, which again we should recognize as Sierpinski's triangle. Now this is more of an approximation, because as you can see, it's not completely filled in just because I don't have enough dots. But the idea is that if I let this run for infinity, this would approach Sierpinski's triangle more and more and more and more. The only caveat to that is the initial dot that I picked might take a while to join these sets of points. Like for example, this point here obviously shouldn't be here. It looks like what happened is that maybe this point was picked, and then I went halfway to C, and then this point got picked. something like that. But eventually, once the points join Sierpinski's triangle, they will stay in Sierpinski's triangle, I think, forever. This is crazy, and I have no idea why this triangle comes up. This little HTML thing I've got here lets me do some other fun things that I will quickly go through. So if I wanted to, I could add, let me just reset this. If I want to add a fourth corner, we run this. Interestingly, we don't really get anything special, it's just a square. It looks like every point can be reached in this space. But if I make it 5 points, now we get another sort of Sierpinskian shape. This is like a Sierpinski hexagon, I suppose, but you see all these gaps in the middle that I think are supposed to be hexagons that aren't being reached. And finally, I can change the rules, so instead of picking my point exactly halfway through the line, let's say I want to make it 70% through the line, and I run that. I still get Sierpinski's triangle, but it's a lot more zoomed out. Every instance of it is more zoomed out, everything's. And only these points are being reached, which is really, really weird. Anyway, that's the third example of where this triangle can come up. Now the final example is to do with a game called Towers of Hanoi. Now the Towers of Hanoi, I'm just going to quickly write that down actually. The Towers of Hanoi is somewhat of a simple game. It involves having 3 pigs and different sizes of blocks. And let's say in a very simple version of the game, we have 3 blocks. And the rule is that you want to pick up blocks and move them to different pigs. So for my opening move, I might pick up this block here and move it to this pig. So now I have the little block down here and it's gone from here, right? The only real rule of Towers of Hanoi is that you can't place bigger blocks onto smaller blocks. So if I moved this small block here, I couldn't then take the medium-sized block and move it here, because then I've put a bigger one on a smaller one. And that violates the rules of the game. The goal of the game is to move the structure from the first pig to the third pig. So in a series of moves, I want to get from this state to the exact same thing over here. Now, how to play and win the game is quite interesting in its own right. It's actually not too difficult, and it's a fun little puzzle. If you go online and look up Towers of Hanoi puzzle game, you can probably play this online. It can get interesting when you add way more pieces or you add more pigs. But how does this relate at all to Sierpinski's triangle? Well, I am getting there. Let's consider a very simple version of the game where we only have 1 block. Right, 1 block. And it doesn't matter what size the block is because there's only 1 of them. And let's consider what states this game can have. Well, there are only 3 valid boards for this game. The block can either be here, which is in position 1, or it can be here, which we'll call position 2, or it can be here, which we'll call position 3. And I can reach any state from every other state. So if I wanted to draw this as a graph, I could say these are my states, and my edges are just going to represent when I can connect from one state to another state. So this is state 1, this is state 2, and this is state 3. Right, seems simple enough. Now what happens when I add a second block? We're going to try and do a similar thing. Well, if I add a second block to my game, we're going to have a lot more states that we can choose from. So we're going to have a big piece and a little piece. And so now I'm going to represent every state with 2 numbers. And let's just say that the first number can represent the the numbers can represent different pieces. So we're going to have 2 numbers in each. So this situation is 1, 1, meaning both pieces are on the first pig. And to win the game, I want to get to 3, 3, meaning they're both on the third pig. Now, I won't draw this out myself, but I have got it pre-written here. I'm just going to bring it over. What would this game state look like? It looks like this. So I've got 2 valid opening moves, and only 2, which makes sense because if the pieces are both on the same peg, all I can do is move the smaller one somewhere else, which is why actually in all 3 of these scenarios, I only have 2 options. But in all the other scenarios, I have 3 options. These all connect to three different nodes. And yeah, this is the game. This is what the game looks like. So again, you can see where I'm going with this. If I keep going, let's have a look at the game when I add a third peg. And this one is a lot better illustrated. This one I haven't made by myself. It's just ripped from Google Images. But this is what it looks like if I added a third block to my game. Oh, what have I done? I don't know why it keeps doing that. Copy and paste. Look at that. That's crazy. You can see here the diagrams here. So again, the letters represent where each block is in the order. This is the starting state, and this is the solution state. So if I wanted to actually solve the puzzle, I would just sort of take any path to get to here. In this case, I would take this path. But yeah, again, Tower of Hanoi. And this is going to keep going as it gets deeper and deeper. So this is actually what's called a Hanoi graph. And a Hanoi graph is represented with an H and then 2 values. This is going to be H33. Now, this number here represents the number of blocks. So there's 3 blocks in this game. And this here represents the number of pegs. Now, if I take H of n blocks with 3 pegs and take the limit as n goes to infinity, this structure is going to approach a Sierpinski triangle. So if I go to 4 or 5 or 6, this shape here is just going to get more and more extreme, and it's going to get closer and closer to this, or an infinitely packed Sierpinski's triangle. Now, actually for experts, that raises the question, what happens if I add a 4th peg? Well, firstly, the game's going to get a lot easier, because there's going to be less restraints on what you can do. But what would that graph actually end up looking like? And can I even really draw it well? And the answer is yes, I can draw it well, and I have an image of it here. I'll quickly have a guess about what it will be before I show the image. It's a pretty low quality image. Here we go. This is what happens when I have 4 pegs. This is the tesseract. What you can see is this is like a 3-dimensional version of my Sierpinski's triangle, and we have 4 ends instead of 3 ends, which makes sense because now there's 4 pegs instead of 3 pegs, because again, each of these ends here represents all the pieces being stacked onto 1 peg. So when I've got 4 pegs, there's 4 ends to my shape. But again, it also has this limiting process where if I keep increasing n, this will get more and more packed. And yeah, that's the 4th and final example of the Sierpinski's triangle being found. So I invite you to have a think about what all these scenarios had in common. The only thing I can really think of that really satisfies me is this idea of evenness and oddness. All of these things involved even and odd, or some idea of something being off and on, or something being true and false. Even in the Towers of Hanoi puzzle, like powers of 2 are deeply intertwined with the Towers of Hanoi puzzle. The idea of you either moving a block or you're not moving a block, this is a very binary idea. But yeah, so that is all for those examples. And I have one more small thing I want to talk about before we end the video, so I'll move on to that now. The final thing I want to talk about is the dimensionality of Sierpinski's triangle. So we talked about a 3-dimensional Sierpinski's triangle and a 2-dimensional Sierpinski's triangle. But depending on how you think about dimensions, Sierpinski's triangle itself might not even be considered a two-dimensional shape. I'm just going to bring that original image back onto the screen. And I'm just going to bring the big one over. Here we go. It's a bit cut off here, but that's okay. Now, keep in mind that one of the main things about this triangle is that it's self-similar. So this triangle here contains a smaller version of itself. Let's have a think about what dimensionality actually means. If I take a square, we can all agree this square is two-dimensional, right? How many squares do I need to build a square twice as big? Well, if I want to build a square twice as big, I'll need to put one here, and one here, and one here. I need 4 more, right? To double the size of my shape. And keep in mind that 4 is 2 to the power of 2. It's going to be important. Now what about a 3D shape? Namely a cube. How many cubes do I need to double the size of my cube? Well, I'm not going to be able to draw this, but if you think about it, you'll see the answer is 8. Because I'm going to need to do like a ground layer of 4 cubes and then another 4 cubes on top of them to make a bigger cube, 2 times the size. And 8 is 2 to the power of 3. Now if I go back one dimension and I have a line and I ask how many lines do I need to double the size of the line, the answer is just 2. I stick a line next to the line, which is 2, and this is going to be 2 to the power of 1. So this is 2D, 3D, and I had 1D here. So as you can see, if we assume this pattern continues, for a 4-dimensional cube, which we can call a hypercube, I'm going to need 16 of them to double its size. For a 5-dimensional cube, I'm going to need 32 of them to double its size. So let's consider this to be the definition of a dimension. It tells you how many of the shape you need to double its size. This is called a Hausdorff dimension. I'm not sure if I'm pronouncing that correctly, but this is just one notion of a dimension. I'm not saying this is actually what like dimensions mean typically when we talk about dimensions. So let's consider the Hausdorff dimension of Sierpinski's triangle. Well, the question is, how many Sierpinski's triangles do I need to double its size? Well, to double the size, this is the height of one of them. This is the height of the whole thing. So this here, if this here was a normal Sierpinski's triangle size, this would be double the size. So how many Sierpinski's triangles do I need to double its size? Well, I need 3. So not quite 4. Now remember, my definition of dimensionality is that it's always going to be 2 to the power of the dimension. Because for 2D, it was 2 to the power of 2. For 3D, it was 2 to the power of 3. And for 1D, it was 2 to the power of 1. Which means that 3 has to equal 2 to the power of the dimension of this shape. Now if I take the natural log of both sides, I get the natural log of 3 times, using the log rules, I can put d out in front, d over the natural log of 2, which means that d is going to equal the log of 3, or the natural log of 3 over the natural log of 2, which equals about 1.585. So if we think about dimensions in this way, we can say that this shape is 1.585 dimensional, which is kind of cool. And a lot of fractals, especially self-similar fractals, are going to have a Hausdorff dimension, and you can calculate what they are, and they're quite interesting. But yeah, I think that's about all I have to say about Sierpinski's triangle. So yeah, cheers. Thanks for watching, everybody.